So now that we have a model, we need some way of knowing where the robot is. Because the state of the robot is x, y, and phi, meaning the position x, y, and its heading phi. Odometry is the means by which we can obtain this pose information. And the question is, how do we actually get the state or the pose of the robot? Well, there are a number of different ways of doing it, but at the end of the day, we absolutely need sensors, right? And there are really two possibilities here. One is we can use some kind of external sensors. So an external sensor would be a sensor that's measuring something in the environment. So for instance, if you pretend that you can see a landmark, let's say I can see the Eiffel Tower. And now I start moving around. If I keep track of the Eiffel Tower, I should be able to at least know where I am relative to the Eiffel Tower. Right? That seems to make some sense. So the external sensors, ultrasound, infrared, cameras, laser scanners, these are sensors that tell us something externally about where we are. There is another type of external sensor that one can use, of course, which would be GPS. And it's external because we're not measuring it internally. We're getting information from outside. And the GPS immediately would give us things like position and so forth. However, when you're running robots indoors, you certainly don't have GPS signals. And a lot of times, GPS alone is not enough to know X, Y, and phi to any high level of fidelity. So what you do is you typically couple the external sensors with internal sensors. So the internal sensors are sensors that are sitting in the robot, and they're helping you know where you are. So for instance, you could use a compass to figure out which way the robot is heading. So this would be orientation. Of course, in every self-respecting robot, there are accelerometers and gyroscopes for finding out how far you've traveled and so forth. So position and orientation can both be derived from accelerometers and gyroscopes to a certain degree. Another useful way is wheel encoders. So typically, you have tick counts. You can tick and count basically how many revolutions the wheels are doing in a certain amount of time. And from that, you can actually figure out things about where the robot is. And I would like to discuss a little bit with you about wheel encoders. And the reason for that is that if we are indeed now working on differential drive robots for a while, let's see if we can find out a little bit of how we can get position information, and more importantly, how much can we trust it. So a wheel encoder, it gives the distance moved by each wheel. So we have left and right wheels here. And here's the following assumption we're going to make. We're going to assume that each wheel is following an arc, which means that it's turning at a constant rate and driving at a constant velocity, basically. So v and omega are constant. What this means is on short time scales, that's correct. And if we do that, well, let's say that d sub l is the distance the left wheel has turned, and d sub r is the distance the right wheel has turned. So in this case, the right wheel is turning quicker than the left wheel because it's turned more. Well, I'm interested in x, y, and phi, which is not where the wheels are, but where the center of the robot is. This is where I'm interested in. So dc is the distance the center has turned, and that's the thing that I'm interested in. Now, luckily, the center is simply dl plus dr over 2. I am not going to be particularly picky in showing where the geometry of this comes from. Instead, these are things that are readily available if you want to look up things like how wheel encoders work. But I want to connect a little bit with the mobile robot model to the wheel encoders just to see how we reason about things. And in fact, if we are measuring how far the wheels have moved over a time interval, so let's say that we start at x, and after the time interval, well, we know dc because dc is this thing, then we can actually compute the new x prime, so the new x position of the robot. We can similarly compute the new y position of the robot, which is the same as the x update, but it has a sine instead of a cosine term. And we can even compute the new orientation. So this is a way of knowing how to go from how far the wheels have turned into what are the new positions of the robot. And in fact, we're going to be running quite a few experiments where the only information the robot has is where it is based on the wheel encoders. So, but how do we know dr and dl, though? This is what we need to know in order to find out where the robot is. Well, assume that each wheel has n ticks per revolution. So 2 pi degrees is n ticks. So most wheel encoders actually give the total tick count since the beginning. So what you measure is how many ticks since you started the system up. So the update, I'm writing it for both wheels. This is for the left wheel and the right wheel. So you could write a little subscript, you know, delta tick R, 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 or L if you want. But for both of these wheels, you take the old total tick count and subtract it away from the new total tick count. So this tells me what's the tick count during the time interval you just looked at. And then based on that, you can very easily compute what the distance that wheel has turned. So this D here, this D could either be D sub L or D sub R. So it's simply 2 pi R delta tick over N. So this actually gives us a way of mapping ticks onto distances traveled. And as we saw in the previous slide, distance traveled, we can then map into new position and orientation of the robot. Fair enough. There is one major disclaimer I must make, though, and that is, chala, drift. A system like this, drift. It's very imprecise, and if you're using only wheel encoders as your source of odometry, you're probably going to run into a little bit of trouble. So here, I want to show a video. This was from one of the courses I taught recently, where you have now 2 robots competing against each other. It looks like they're following lines, but all they're doing is following waypoints that laid down, and they're using a PID regulator to get to the waypoints. And what you can see is that they're getting a little bit out of whack. And the interesting thing here is one robot gets up on top of the other robot, and as a consequence, the wheel is spinning without it's actually touching the ground. And as you can see, the robot then has a completely confused idea of where it is in the world. So this would be an example of where drift is rather severe, and the robot is going in way wrong direction because of the fact that the wheel encoders no longer correspond to what's happening on the ground. So we're going to use wheel encoders a lot. They're used a lot in robotics, but we always need to be aware of the fact that by themselves, wheel encoders do not tell the full story or a particularly robust story.